Action potentials. Now you're going to get to look at a little electrical reading of them. So, a couple of rules to remember. Action potentials only occur in axons. Graded potentials, rather than an action potential, occur in dendrites. Action potentials, we're going to need a lot of room on here, are generated, another word for started or initiated, at the axon hillock if threshold is reached. That is determined by the summative graded potentials coming from the dendrites. Then, okay, so that's one key idea. Then the action potentials is propagated, basically regenerated, at each node of Ranvier. Okay, now if all of this seems a little confusing, here's another helpful point to write down, is that electrical changes in cell membranes occur by ions, specifically sodium and potassium, entering or leaving the cell. Look at it this way. If a bunch of sodium ions enter the cell, now the cell's more positive. If a bunch of potassium ions leave the cell, well, now the cell is more negative. So it's a relative thing. Are there relatively more sodiums coming into the cell or potassiums leaving the cell? If more sodiums are coming in, now depolarization is happening. If potassium ions are leaving, now repolarization is happening. So let's go ahead and look at the parts of one action potential. On the y-axis, you can write membrane potential. And the tip top that matches with the top of the action potential is going to be about plus 30 millivolts. And then the bottom that matches up with the resting potential, like the way the cell is when it's not firing an action potential, that's going to be about minus 70 millivolts. So look at the change. Minus 70, and then it's got to go up to 0, right? And then 30 more. So what's the total change? You go up 70 plus 30 more, a total change of 100 millivolts. Then there's this important point right about here where you see, it looks like it was thinking about it, and then whoosh, up it goes. That tells you that's where threshold is. So that number is usually about minus 55 millivolts. So a graded potential all of the graded potentials have to get the cell from minus 70 to minus 55. And that means enough sodium ions coming in that the cell reaches minus 55, at which point there's sort of a trigger inside of the cell and all of the sodium channels will open. Okay, let's go ahead and look at the first part, the resting membrane potential. Right about here at minus 70, I'm using blue for that. Oh, I forgot to put time. Sorry. Time in milliseconds. Usually an action potential takes about 150 milliseconds. Okay, now back to your blue pen for part 1. We're going to have a total of 5 different steps. Okay, so the resting membrane potential is about minus 70 millivolts. It's maintained by the sodium-potassium ATPase pump. So that is a pump that uses ATP to keep the inside of the cell negative. We call this part, the way that the cell is here, polarized. Polarized means to have opposite sides, right? Like you have a north pole and a south pole. Well, in a cell, what that means is the inside of the cell is very negative and the outside of the cell is not. And so how does this pump work? Well, if these are both positive ions and it were, let's say, to put one sodium out and one potassium in, that's not polarized, is it? It must have an imbalance. And sure enough, what happens are 3 sodiums are pumped out and 2 pumped in, and that does 2 things, 2 important results of this. Number 1, this means that sodium in our bodies is always and very more concentrated outside of your cells. Like, for example, in the blood, too. And conversely, potassium always and very more concentrated inside. And one way that I remember this is that if you were going to have a margarita, you would put the sodium chloride, salt, on the outside of the glass, right, on the rim. So sodium is always more concentrated outside. And the potassium is always concentrated inside the cells. And then the other natural occurrence that happens because of this pump is that, relatively speaking, then, where is it more positive? Well, outside, because 3 sodiums are pumped out. Oops, I forgot to put 2 potassiums. And 2 potassiums pumped in, so there's more. If you just said 3 positives are pumped out and 2 positives are pumped in, what that means is it's more positive outside and more negative inside. In fact, minus 70 millivolts negative on the inside. Okay, now the next thing to note on our picture are graded potentials. We can put those in pink. These are the little hills that went up, and then this was even a graded potential, but it was a big enough graded potential that an action potential did end up getting fired. So, and using your blue pen, you can put, here's number 1 for resting, and then number 2, graded potentials. May or may not make the grade. These are coming from dendrites. arriving at the axon hillock. If they are not strong, no action potential is fired. So you can see that these two were not strong enough. The graded potentials coming down the dendrites to the axon hillock were not strong enough EPSPs summatively to fire an action potential, whereas this one was, and then something different happened. And that difference is now what we call depolarization. So you can use a green highlighter and watch this. Ooh. So you're going to go up, up, and away. And put a number 3 on what's happening here. And call this depolarization. The polarized state has been taken away. Okay, so what's happening at this point is that when threshold is reached, like I said, it's like a button or something gets pushed in the cell, and at this point, now all the sodium channels say, what the heck, we're all opening, threshold was reached. So all the sodium channels open and sodium rushes in. Why is this? Why is it the sodium enters? Why doesn't it leave? Well, the secret is right here. Sodium in our bodies is always and very more concentrated outside of the cells. So according to diffusion, sodium wants to go from its area of high concentration outside of the cell to its area of low concentration inside the cell. So with all the sodium channels open, then the potential goes up to plus 30. And now the doors shut rapidly. So there's still more sodium outside of the cell than inside. It's just that for just a brief moment in time, the sodium was allowed to do what it wants to do, which is to come in. Okay, now meanwhile you might be wondering, well, how are we going to go back down? Or maybe you're wondering, where does potassium come into all of this? It comes in right here. It's the reason you go down. Whoosh. All the way down is thanks to potassium. So this is step 4. We call this repolarization. At this point, potassium doors open, the channels. Okay, now we can ask the same question. We can ask 2 questions first. Well, why did the potassium doors open? Well, it turns out that the potassium doors are triggered to open when the membrane potential is positive. So it works out quite nicely, right? The membrane potential gets positive, and then the potassium doors respond by opening. Potassium leaves the cell, but as it's leaving the cell, that means positive is going bye-bye, right? So as positive goes bye-bye, negativity increases and you go down, 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 down. And then the next part to make sure you understand is, why does potassium leave? Why doesn't it enter? Why doesn't it make the cell go from plus 30 up to plus 60? And the secret, again, is thanks to that ATPase pump. Potassium is always and very more concentrated inside the cells. So it wants to follow diffusion. If a channel opens in the membrane, potassium goes from its area of high concentration inside the cell outside to its lower concentration outside of the cell.